Preparing for a physical design engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. What is the physical design flow, and where do the major closure challenges occur? Physical design converts synthesized logic into manufacturable layout. I begin with floor planning, power planning, placement, clock tree synthesis, routing, and sign-off. At each stage, I use timing, congestion, power, and area reports to guide optimization rather than treating steps independently. A good flow preserves constraints, validates extracted parasitics, and closes DRC, LVS, STA, IR, and M checks. The core challenge is balancing PPA without sacrificing manufacturability. While answering, outline synthesis handoff, floor planning, power planning, placement, CTS, routing, extraction, sign-off, and the interactions among timing, congestion, power, area, DRC, LVS, IR drop, and electromigration. Question 2. How would you create an initial floor plan for a large society? I start by understanding hierarchy, macro dimensions, interface pins, voltage domains, clocking, and critical timing paths. Then I choose a reasonable aspect ratio and utilization target, place large macros near related logic and boundaries, reserve routing channels, and align power connections. I leave white space around macros and congested interfaces for buffers and feed-throughs. Finally, I run early global placement and congestion analysis, iterating before detailed implementation makes changes expensive. Make sure to cover die and core dimensions, utilization targets, macro placement, aspect ratio, pin locations, hierarchy, channels, blockages, routing resources, power grid access, and early congestion or timing estimation. Question 3. What factors influence standard cell utilization, and how would you respond to excessive congestion? Utilization is not simply the percentage of occupied core area. Routability depends on pin density, macro boundaries, available layers, and buffering requirements. If congestion is excessive, I first locate hotspots using global route maps, then check macro placement, narrow channels, high fan-out logic, and over-constrained regions. I may reduce local utilization, add halos or partial blockages, spread cells, move macros, or improve hierarchy. Lowering average utilization alone may not solve a localized bottleneck. Discuss utilization versus routability, macro halos, placement blockages, pin density, cell padding, layer resources, timing critical regions, buffering demand, power effects, and iterative floor plan or placement refinement. Question 4. How do you design a robust power distribution network? I design the power network from current demand and package connectivity outward. I establish rings, robust vertical and horizontal straps, sufficient via arrays, and appropriate connections across voltage domains. Strap pitch and width must control resistance without consuming excessive routing resources. I analyze static and dynamic IR drop, then check electromigration under realistic activity and corners. Weak regions usually require additional straps, vias, power pads, or improved placement, not merely wider local wires. In your answer, mention rings, straps, mesh topology, layer assignment, via arrays, voltage domains, current demand, rail resistance, IR drop, electromigration, pad locations, and dynamic versus static analysis. Question 5. What is the difference between setup and hold timing, and how do you fix each violation? Setup verifies that data arrives before the capture edge, so it is a maximum delay problem. Hold verifies that data does not arrive too early after that edge, making it a minimum delay problem. I fix setup with stronger cells, shorter routes, reduced fan-out, better placement, or beneficial skew. I fix hold by adding delay, downsizing cells, or adjusting skew. Every fix must be rechecked across MCMM corners because setup and hold changes can conflict. Be sure to explain launch and capture edges, maximum and minimum delay, clock skew, setup and hold equations, useful skew, data path optimization, buffering, cell sizing, and the risks of fixing one check while harming another. Question 6. Explain clock tree synthesis and the goals of a good clock network. Clock tree synthesis distributes the clock to sequential sinks while controlling skew, latency, transition, power, and variability. I provide accurate clock definitions, sync constraints, gating information, and routing rules, then inspect balance, insertion delay, transition, and buffer count. A useful tree may intentionally introduce skew to improve setup, but excessive skew can damage hold and robustness. I also verify clock gating checks, propagated clocks, shielding, and extracted post-root behavior. Cover insertion delay, skew, latency, transition, clock uncertainty, sync balancing, useful skew, clock gating, NDRs, shielding, clock cells, and post-CTS timing or power trade-offs. Question 7. How would you debug a large number of post-CTS hold violations? I first confirm the violations are real by checking propagated clocks, active corners, uncertainty, and generated clock definitions. Then I cluster paths by physical location and inspect whether negative skew or very short data paths is the dominant cause. I prefer targeted delay cells, downsizing, or controlled route detours, while protecting setup and congestion. If violations are widespread, I revisit CTS targets or skew balance instead of inserting thousands of buffers blindly. Focus on violation clustering, early and late corners, clock skew, short data paths, ideal versus propagated clocks, useful skew, delay cell insertion, route detours, transition, and avoiding excessive area or leakage growth. Question 8. What causes routing congestion, and how do you resolve it without damaging timing? Congestion usually comes from dense placement, poor macro channels, pin access limitations, excessive buffering, high fan-out nets, or restricted routing layers. I identify whether overflow is global, local, or pin-related using congestion maps and route guides. Remedies include moving macros, spreading cells, reducing placement density, adding partial blockages, promoting selected nets, and improving pin access. I apply timing-aware changes because a congestion fix that lengthens critical paths can simply transfer the problem. Mention macro placement, utilization, pin access, high fan-out nets, layer constraints, blockages, clock routes, detailed router overflow, cell spreading, buffering, layer promotion, and timing-aware optimization. Question 9. How do you approach timing closure in a multi-corner, multi-mode design? I begin by validating modes, clocks, exceptions, libraries, RC corners, derates, and scenario weights. Then I identify the worst setup and hold paths by functional relevance, separating true root causes from constraint or reporting issues. I optimize shared logic carefully because a change helping one corner may hurt another. I use path groups, common path pessimism removal, incremental analysis, and regression tracking. MCMM closure succeeds when every fix is checked across all meaningful scenarios. In your answer, discuss scenario definition, libraries, RC corners, operating modes, path grouping, dominant corners, common path pessimism, derates, prioritization, and avoiding optimization that regresses other scenarios. Question 10. What are false paths and multicycle paths, and how do you validate timing exceptions? A false path is functionally never sensitized, while a multicycle path is allowed multiple cycles for data transfer. I never add either exception merely to improve reports. I validate the functional protocol, identify precise start points and endpoints, and confirm clock relationships. For multi-cycle setup, I also handle the corresponding hold requirement correctly. Finally, I review exception coverage with timing reports and, where possible, formal or simulation evidence, because broad exceptions can hide silicon failures. Explain the intent of each exception, start point and endpoint selection, set up and hold implications for multi-cycle paths, asynchronous crossings, generated clocks, reports, formal validation, and the danger of masking real timing failures. Question 11. How do parasitic extraction and RC variation affect timing signoff? Parasitic extraction converts routed geometry into resistance and capacitance values used by signoff timing. Long wires, vias, coupling, and layer choices can substantially change delay compared with placement estimates. I review extracted SPEF quality, RC corners, coupling settings, and correlation between implementation and signoff tools. Crosstalk can create both delay shifts and noise failures, so shielding, spacing, or rerouting may be necessary. Timing closure is not complete until extracted. Variation-aware analysis is clean. Be sure to cover wire resistance and capacitance, SPEF, extraction corners, coupling capacitance, crosstalk delay, noise, route topology, signoff correlation, and differences between estimated and extracted timing. Question 12. How would you analyze and mitigate crosstalk-induced timing or noise violations? I identify the victim net, dominant aggressors, coupling capacitance, alignment of transitions, and whether the failure is delay or noise related. I first consider physical fixes such as increased spacing, shielding, layer changes, shorter parallel runs, or rerouting. Buffering or resizing can improve transition but may increase power and congestion. I verify the result with extracted crosstalk analysis across relevant switching patterns, since a visually separated route is not automatically electrically safe. Discuss aggressor and victim nets, capacitive coupling, delta delay, noise glitches, transition, shielding, spacing, layer changes, buffering, net ordering, victim sensitivity, and signoff noise analysis. Question 13. What are antenna violations, and how do you fix them? An antenna violation occurs when a partially fabricated metal structure accumulates charge and damages an attached gate oxide during processing. I inspect the violating net and rule ratio, then use antenna diodes, layer jumping, rerouting, or segmentation to reduce exposed conductor before the gate is connected. Diodes are effective but consume area and add leakage or capacitance. I choose the least harmful fix, reroute when practical, and rerun signoff antenna checks after final connectivity changes. Mention plasma charging during fabrication, exposed metal to gate ratio, partial routing, antenna rules, diode insertion, jumper layers, routing changes, diode leakage, area impact, and final signoff verification. Question 14. How do you distinguish and debug DRC, LVS, and connectivity failures? DRC checks whether layout geometry obeys manufacturing rules, while LVS compares extracted connectivity and devices with the schematic or netlist. I classify errors by root cause instead of fixing markers independently. For DRC, I inspect spacing, width, enclosure, via, and density context. For LVS, I trace opens, shorts, missing devices, incorrect pins, or extraction mismatches back to the layout. After each structural fix, I rerun connectivity and signoff checks to prevent cascading errors. Explain geometric design rules, layout versus schematic comparison, opens, shorts, missing vias, pin mismatches, abstract issues, hierarchy, error clustering, incremental fixes, and clean reruns after database or netlist changes. Question 15. What is the purpose of engineering change orders, and how do you implement a safe timing eco? An eco makes a targeted design change after the main implementation flow, often to repair timing or functionality without restarting everything. For a timing eco, I identify the failing path, select spare or available cells, resize or insert logic, and perform incremental placement and routing. I preserve stable regions, then rerun SANTA across MCMM scenarios. Formal equivalence, DRC, LVS, antenna, IR, M, and final connectivity checks are essential because a small change can create broad regressions. Cover functional versus timing ECOs, spare cells, metal-only changes, incremental placement and routing, setup or hold impact, equivalence checking, DRC, LVS, IR, M, and regression discipline. Question 16. How do you address electromigration and IR drop violations late in the flow? I first determine whether the failure is static IR, dynamic IR, or electromigration, and whether it is localized to a rail, via, strap, or cell cluster. I validate activity and thermal assumptions before changing layout. Typical fixes include wider or additional straps, more vias, stronger pad connections, spreading high current cells, decoupling insertion, or reducing local switching. I then rerun timing and congestion, because power grid reinforcement consumes routing resources and can alter parasitics. Focus on current density, voltage drop, static and dynamic analysis, power straps, vias, cell spreading, decoupling, activity assumptions, thermal effects, metal width, and timing impact of corrective changes. Question 17. How do low power techniques such as multi-voltage domains affect physical design? Multi-voltage design adds physical requirements beyond ordinary placement and routing. I create voltage areas, place level shifters and isolation cells at legal boundaries, provide always-on power connections, and support retention and power switch structures where required. UPF must match implementation intent, including supply nets and domain behavior. I also check crossing legality, isolation control reachability, IR drop per domain, and low power verification. Early domain-aware floor planning prevents difficult late-stage movement and routing. Discuss voltage areas, level shifters, isolation cells, retention cells, power switches, UPF intent, always-on routing, domain crossings, placement constraints, power grid separation, and low power verification. Question 18. How would you reduce physical design power while maintaining timing and area targets? I separate dynamic power from leakage before optimizing. For dynamic power, I reduce switching and capacitance through clock gating, shorter routes, lower fanout, better buffering, and glitch reduction. For leakage, I use high threshold cells on non-critical paths and power gating techniques where architecture supports them. I protect timing by reserving low threshold or larger cells for genuinely critical paths. Every change is evaluated with realistic activity, MCMM timing, IR, area, and reliability reports. Mention dynamic and leakage power, clock tree power, switching activity, cell sizing, high threshold cells, voltage islands, clock gating, glitch reduction, capacitance, buffering, and trade-offs with timing and reliability. Question 19. What physical design checks are required before tapeout, and how do you prioritize failures? Before tapeout, I expect clean signoff SANTA across MCMM scenarios, DRC, LVS, antenna, density, extraction, crosstalk, IR drop, electromigration, power intent, and equivalence checks. I prioritize failures by silicon risk, functional connectivity, unbounded timing, power integrity, reliability, and manufacturability usually come before cosmetic warnings. Each waiver needs technical justification, ownership, and evidence. I also confirm final database consistency, stream out validation, reports, scripts, and reproducibility for the exact released design. Include signoff STA, DRC, LVS, antenna, density, IR drop, electromigration, crosstalk, metal fill, power intent, equivalence, reliability, waivers, reproducibility, and documented risk-based closure. Question 20. Describe a physical design failure you would investigate and how you would drive root cause analysis. I would begin by reproducing the failure from the exact database, constraints, tool versions, and corner. Next, I would classify the symptom, timing, congestion, power integrity, or DRC, and correlate reports with physical locations and recent changes. I would test one hypothesis at a time, using incremental reruns to preserve evidence. After identifying the root cause, I would implement the smallest robust fix, document it, communicate dependencies, and add an earlier check to prevent recurrence. Be sure to explain symptom isolation, report correlation, database inspection, hypothesis testing, change control, cross-functional communication, regression checks, root cause, corrective action, and process prevention. If you are still with us, congratulations! You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.